Good afternoon and welcome to today's Military and Aerospace Electronics webinar titled Managing Signal Integrity Challenges for Success in High-Performance Embedded Computing Systems. Today's event is sponsored by Elma Electronic. I'm Jamie Whitney, Senior Editor of Military and Aerospace Electronics with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical questions during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Military and Aerospace Electronics website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speakers for today's discussion. Mark Littlefield is the Director of Systems Products for Elma Electronic, and Frank Lefebvre is Director of Technical Sales at Interface Concept. Welcome, Mark. The floor is yours.
Thank you, Jamie, and thank you everyone for joining us today. I'm excited to talk about this topic. It's an interesting topic. We'll be talking about managing signal integrity challenges in high-performance embedded computing systems. In my lead-off, I'll be focusing mainly on the new VITA 68.3 standard that's in work and talking about some of the aspects of that. So on to my first slide. Oh, that's the bumper slide, so let me go ahead and press on from there. So we're going to be focusing on VPX, as that's kind of the platform du jour that most of these high-performance embedded systems are being built on today. In the years since its introduction in the mid-2000s, the bandwidths that are expected to be passed from board to board over the backplane have grown by an order of magnitude. So it's a much tougher problem today to be able to have boards and backplanes from different vendors play well together, if you will. So the communications channels that are generally desirable today are 100 gig Ethernet and PCI Express Gen 4, at least at the highest end of the systems. And these are pretty high-speed channels, and they, as a result, have significant challenges for VPX. The introduction a few years ago of the RT3 connector basically opened the door and made these speeds possible, but the connector alone doesn't guarantee that you're going to get that kind of performance. The RT3 is a smaller diameter, has smaller diameter vias than the previous RT2 connector that results in better return loss. That's a big part of what makes it support these speeds. Also, the footprint geometry of the connector means crosstalk still remains a concern, especially with thick PCBs. There's other common problems of insertion loss, return loss, crosstalk at higher frequencies that RT2s had to deal with. And so the issue of end-to-end channel design really starts to play a significant role. In fact, it really is a significant role in modern systems. So basically, a design needs to be validated before it's fabricated and then put into the field. The only way to do this is through extensive simulations and measurements, and then ideally followed by simulation to measurement correlations to make sure that the assumptions that you made within the simulation are correct. So how do you do this? How do you do this end-to-end simulation with boards and backplanes from different suppliers? Well, the short answer is you can't, unless you have a common reference model that everybody agrees on. And at this instant in time, we don't have that in the market. So several years ago, Elma said, okay, well, we need to solve it for ourselves and for our partners in our supply base to try to come up with something that we all can start to agree on that, yeah, this does what we need it to do. So several years ago, we did about an 18-month study and developed the tools and methodologies that we needed to be able to reliably support communications at these speeds. And so the result was that we have a reference model that we were able to apply to backplane development, and we shared this model with others and what have you to try to build up an infrastructure. And if you want to learn more about that, I actually gave a talk about 2 years ago, March 22, on that topic, and the link is at the bottom of the page there. However, that's not an industry standard model, and it really didn't solve the problem for us or for everyone. So VITA 68.3 was started. Now, what VITA 68.3 is, it documents a reference model approach for OpenVPX signal integrity compliance at baud rates above 10.32125 gigabaud. It defines a reference S parameter model, in fact, several models, which vendors need to use to with their own models to simulate that end-to-end channel. So if you're making a plug-in card, you need to then use the models for the backplane and a target plug-in card as a reference when you're testing your design. And boiling down a sizable document to a few key bullets, it basically provides two options for doing this. You have a full test suite, which is 150 or more different permutations that of various parameters that you would adjust to basically check out your channel integrity. Basically working all of the various dark corners, if you will, the corner cases to make sure that there's no gotchas. And this includes the high Z maximum loss VPX backplane design, along with a high Z long VITA 68.3 reference models at both ends. Signal integrity compliance to this standard is basically, for a plug-in module or a backplane, is based on that simulation of the end-to-end channel against the requirements of the applicable protocol. So it depends on exactly which protocol you're planning to use or want to qualify against. Adjust with the steps that you take a little bit. So where 68.3 came from was actually two previous standards efforts in VITA 68 in the working group. So you have ANSI VITA 68.1. This provides signal integrity budgets for interoperability, but it was limited to the RT2 connector, and its speeds were limited to 10.3125 gigabaud, and lower rates. Then later, 68.2, ANSI VITA 68.2 introduced standard S parameter models for mezzanines, modules, and backplanes. But again, it's still RT2 and still limited to those lower rates. With the introduction of the higher speed protocols, we really needed a set of reference models to establish a true baseline to be able to support those higher bandwidths. So work started in late 2021 to establish this reference model when we kicked off the VITA 68.3 working group. And since that time, the working group's been working pretty diligently at it to write that document and define the models. So I'm not going to naturally go through all of the deep, dark corners of the document, but I did want to highlight a few key things that are important in the VITA 68.3 document. Number one is this concept of effective return loss, or ERL. This concept was introduced by IEEE 802.3 CD, which basically defines 50, 100, 200, and 400 gig communications. But it was introduced by Richard Belitz from Samtec. And I put a link here to a very excellent presentation that Richard produced and has available on the Samtec website that goes into a lot more detail than I could ever hope for here. Basically, it's a measure of the losses caused by additive reflections within the channel. And those losses or those reflections are basically from the various connector interfaces from one plug-in card to the next, passing through the backplane. This is all computed in the time domain. And this is a particularly important measurement because of the much smaller margins that are in the PAM4 signaling used by 100 gig Ethernet and PCI Express Gen 4. The next concept is this idea of channel operating margins, or COM. This measurement was introduced by IEEE 802.3bj around 2014, and it's essentially a signal-to-noise ratio figure at a particularly defined bit error rate. This is computed again in the time domain, just like the ERL, and it basically lumps together the insertion loss, the crosstalk, the intersymbol interference, and the receiver and transmitter characteristics to give you a common measurement. And then lastly, and this is probably familiar to a lot of you folks, is the PCI Express channel IMAST. This is a long used method of measuring signal integrity for PCI Express. It basically defines how small a signal can be at the receiver and still be able to be decoded. The eye diagram is basically obtained by taking millions of bits of signal response and superimposing them to form what's called an eye. And then the mask defines whether or not the eye is conformant or not. This is basically determined in the height, which is in millivolts, and the width, which is a unit interval, or UI, which is basically the time of the derived eye. And again, PAM4 makes this a little bit more difficult because PAM4 has multiple levels, multiple voltage levels, as opposed to non-return to zero, which only had the 2 voltage levels. 4 levels mean you basically need 3 eye masks to fully characterize this. So where are we today with 68.3? It's in the stage of basically finalizing the text for the ballot. At this point, I think everybody feels that either all or nearly all of the serious issues are resolved. As I mentioned, it defines 2 compliance options: a recommended or full compliance option, and then the basic compliance option. In the basic compliance option, it is much fewer, can't say that, but it's fewer simulations are required to meet that. But an additional 10% margin on COM and the eye width and the eye height is needed, basically to give a little extra margin on the data to account for not actually testing every single corner case that's possible. The standard does not address certain things, though, like material loss. Depending on your fabricator and your fabrication technique and the materials you choose, material loss is going to be dependent on those things. As a supplier, one has to work with vendors to create test coupons and start basically a statistical database to look at loss variances through production. In addition, you have loss over temperature, variations in loss over temperature, rather. This requires some post-production testing, usually by the fabricator, and the vendor needs to then supply to the fabricator what target losses they expect, and this is usually in dB per inch. And the last thing is again, this is moving towards release for trial use this summer. And I'm going to talk about that a little bit more in the next slide. So rather than go immediately from VITA to an ANSI process to get it approved by ANSI, the working group decided to release this for trial use first. And I think it's a wise choice because it then gets the document out into the world, lets people exercise it, and really kind of figure out whether or not it's solid and whether it needs any adjustment prior to going to ANSI for final approvals. Along with the document will be the S parameter models and the overall methodology, naturally, that vendors would then use to do their end-to-end simulations with their product in the mix. And what this actually means then is that integrators can more easily rest assured that the vendor base is supplying product that will work. It'll just work. Whether it's a plug-in card or a backplane that you can use a plug-in card from one vendor to a backplane to with another vendor, perhaps to another plug-in card from a third vendor, and with a reasonable assurance that they'll talk fine together. What this means for everyone is lower costs and lower prices. There is more work upfront for the hardware vendor, but there's going to be lower support costs and certainly lower costs for the integrator. Trying to debug issues or having to push to respin a backplane or respin a board to deal with an issue that pops up out in the field. So as I mentioned, we have our own methodology, and we've been working with our partners on that methodology. And so as a result, we have a very wide selection of 25 gigabit ready SOSA aligned 3U backplanes available. In fact, the largest selection on the market today. And we have both development chassis like our compact frame or rugged chassis that you can use these backplanes in with assurance that they'll work to solve your problems and work at the speeds that are advertised. So I'm going to wrap up. So VITA 68.3 is really an effort to ensure interoperability between products. Summary vendors run through enough cases using either measured or simulated S parameters on their own products, cascaded with the reference models provided by the standard models of the other channel components. Yeah, the other things that are needed for that end-to-end communication. And then lastly, this pretty clearly shifts the burden of interoperability from the integrator to the supplier of the backplanes and the plug-in modules. And this is what we want from the market. We don't want integrators having to do this at all. With that, I'm going to pass it over to Frank. Oh, I did forget to mention at the beginning, I have one of my colleagues here, Ovidio Messasan. He's our subject matter expert on this topic, so he'll be helping with the Q&A. So Frank, over to you.
Thank you, Mark. Thank you for this very nice presentation. So in the continuation of your presentation, sorry for that. In the continuation of your presentation, we will try to explain what are all the challenges to undertake at the board or plugin module level, and show implicitly how the VITA 68.3 standard will be useful. Currently, of course, all the constraints imposed by the embedded market in our domain, combined with the rapid development of the technologies, are driving the developers to, of course, develop more expertise in the signal integrity domain and implement more new tools in the development chain. So, if we take the example of the next generation or of the new generation of single board computer or Ethernet switches that provide a huge number of 25 gig or 100 gig Ethernet connection, basically supporting 25 gigabits per second SerDes, we see that the complexity of the design dramatically increased when we moved from the old generation of product we introduced 10 years ago, products that was supporting 10 gig and 40 gig Ethernet, to the new products that we are now marketing. The first big change is the speed of the interfaces, of course. We still implement on the board the legacy USB and SATA and Ethernet interface, but the product supports now more and more rapid interface like PCI Express Gen 4 and Gen 5. And of course, 25 gig Ethernet and 100 gig Ethernet. So EC is currently offering, for example, products supporting something like more than 24 lanes at 25 gigabits per second. And this is possible because of the latest technology of the electric material, but also thanks to a very strong control of the routing methodologies. Connected to this change, the chip like processor, FPGA, and Ethernet matrices and transceiver are more and more powerful, more and more capable in terms of functionalities, but in the same time, they are getting larger with respect to their size, heater, and require more and more power supply. Obviously, each of these features has a direct impact on the board layout and PCB design. Just for an example, implementing on the 3U form factor an Ice Lake D, a new generation Intel processor like an Ice Lake D HCC has a direct repercussion on the PCB stack up, since the processor requires something like 8 voltage rails that have to be shared out through 6 separate layers in the PCB. So in addition of that, as I explaining a little bit in the earlier presentations I did some years back, the parts heat dissipation influence a lot the placement of the components on the PCB, and also the routing method that we will point a bit later. The consequence is that the PCB complexity increased dramatically. 24 layers in a PCB becomes more or less the norm. Having several rapid signal crossing other lines is usual. Checking the coupling between the plane and the signal has to be performed at the daily basis when we are designing the board. So this I show this image because to us it's this image really well represents the evolution that we have to integrate into our approach and development process over the last past 15 years. Always keeping in mind that, and I have to say it, that the three fundamental objectives are to make high quality boards, high quality products that comply with their initial specification. In other words, we aim to make sales and deliver boards that are working perfectly for the environment they have been designed to. Mastering the development cost and eventually the recurring cost. We are making custom of the cost of the shelf products. So I mean that have to meet their market. So the price is a very important driver for the COTS product. And eventually we have to be in phase with the time to market. The reality is that the design cycle are longer, the production are also a bit longer now, but we have still a market that expecting the board and the product at the proper time. So we have to be in time. So the big question of this slide is how we move from a mountain bike on the road in the countryside to a Formula One. So Formula One on a highly technical circuit in an urban area, accepting the same level of risk. And so today the answer is definitely the signal integrity simulation. Sorry for that. I'm sure that everyone knows what is a PCB, but a print circuit board is an electronic assembly that use copper conductors to create electrical connection between the components. So this is a basis. And as we said earlier, these copper conductors or signals are more and more numerous on a modern board, and also have to support faster, let's say, has to be faster. Okay. In that way, the coupling of or the energy transfer between these lines or between the signals and the power planes may have negative effect on the line's impedance quality. These negative effects could be seen during the functional test of the prototypes, of course, but we'd rather have to anticipate and correct them at the earlier stage. We can indeed, during the design phase, use the signal integrity simulation tools to make sure that the rapid SerDes are properly routed, maintain the same level of impedance all along the lines, from the component to the connector, for example, make sure that we comply with the recommendation of the standards like VITA 68.x. And we have to ensure that we will be able to have and provide good S parameters to the integrators. These data, like the eye diagram you have in front of you, are simulation at the simulation level are really useful to monitor the channel compliances. They make possible the measurement of a large number of factors likely to simultaneously affect the behavior of the signals, and thus highlight potential error and loss at the level of the channel or interface. Then the goal of signal integrity simulation is to prevent the impedance breaks for us, for interface concept, insertion and return loss issues, and eventually to prevent as much as possible the material loss at the end of the development cycle. So eventually integrating signal integrity simulation in the process and in the organization is essential now. The pre-layout, while the pre-layout SI integration may be interesting, the post-layout simulation is much more essential. Actually, during this phase, exchanges between will be the most sustained between the SI engineers and the routing engineers. Various tools will be implemented. Many analyses will be performed, driving to several adjustments on the PCB routing and the PCB specifications. The simulation will also have an impact on the PCB manufacturing process, and then the PCB specification often gives rise to discussion between engineers and PCB manufacturer, especially on the stack up, of course, the process, how to build the PCB, and sometimes on the dielectric material, while nowadays we know that the Mectron 6 is commonly used and really makes the job. The price is also a topic of or a subject of discussion with the PCB makers, and the price could be eventually a driver in the PCB definition and specification, and it's a good part of the discussion, but not the main part. Finally, at the end of the process, when the hardware engineers receive the prototypes and do the functional tests, it is recommended to compare the real measurement, the real S parameter with what we did earlier during the simulation, and of course report the result into the model if necessary. Sometimes a new run of simulation analysis could be required if a PCB cleanup is required or necessary to make sure that the board will be, let's say, industrializable. So with time and experience, with failure and success, we all establish habits and routines. And there are, of course, rules and processes that we must comply with, but engineers, the engineers also develop expertise that should not be neglected in this domain. They can see what is risky, what will work, and what will not work. In any event, we naturally implement good practices when we design the boards. We, for instance, know that the microstrips are sensitive to the environment, temperature, humidity, dust, and we will rather avoid to place them on the top and on the bottom of the board. The vias are drill hole allowing signals and power to travel between the PCB layers. There are several types of vias. There are several vias on the board, and also several types. And so we have to use these smartly these vias. So, and then, for instance, the VITA pad could be intensively used in high-density PCBs when several BGA are set up on the board. We know also that when the vias comes on the top and on the lower layer of the board, the back drilling is strongly recommended to avoid, the antenna effect that could disturb the signals crossing this area. So what can I add here? And regarding the back drill vias, we are also trying to make it as short as possible. Something that is interesting with the technologies of VIA also is the boomerang VIA. That is really an interesting method to take advantage of the stub by prolonging the signal to address another PCB layer. This technique is particularly suitable for connecting fast signal to the VPX press fit connectors. Given that the press fit connector pins are entering the PCB by a couple of millimeters. In that way, we avoid to route fast signals on the top layer of the PCB connector, since pins could generate stubs. Also, special care has to be considered when differential pairs are going around the antipad. The antipad are rarely numerous on the board and are necessary to ensure the electrical isolation of the connector pins or the component pins. And since differential pairs or rapid signals can come around, so we have to be careful on that. So we are implementing using a modern PCB, and for us, a modern PCB is an electronic card that is that has some room on the bottom and on the top layers in order to place the parts, but also it's a PCB with at least 20 or 24 layers. Several signals to connect the parts and the connector, several vias to cross the layers, but also GND plans, ground plans, and power supply plans that are quite numerous in the modern products. And so all that plans, signals, via could interact with each other and generate unexpected coupling between them and energy transfer. This coupling could be really challenging to highlight with a simulation, but some tools are available and could allow to raise some indication for raising some solution. So integrating signal integrity simulation in the organization means obviously to invest in tools. With respect to the simulation, several solutions are of course available on the market coming from different vendors. They propose various tools at different cost. Here I have to mention that I refer to the functionality supplied by ADS. But whatever is the selected solution for let's say for implementing the system integrity, the signal integrity simulation, it is important to be able to generate the S parameter. This is a must. They are used to describe how power ratio can propagate through signal and electronic PCB. It is an essential tool to the integrators in order to them to generate their own S parameters and make sure that the signal will be good all along the path. As explained, the TDR allows to observe the impedance evolution along the transmission line. The goal is to see the variations that could drive to routing issues and eventually to loss impedance and then to bad signals. With a function like the DC IR drop module, we see if there is a voltage drop at a transistor level. And when that happens on the critical path, it can also lead to a functional failure. So we'd rather prevent it at the simulation level. In the continuation of what I showed in the previous slide, we realize that how important is the rapid scan. The rapid scan could, because the rapid scan could be used to check the current return paths. And so we can anticipate the coupling between the plan with these functionalities. And similarly, with the decap top team, that is an interesting function, will eventually provide. It will eventually provide information about the what we can call the usefulness capacitor we already placed on the board. If we can remove a useless capacitor, so we leave room to something else, and we probably avoid some disturbance on some rapid signals coming around the capacitor. And finally, the PDN calculation. I'm sorry, I wrote it in French, but the PDN calculation helps to adjust the power plan and provide information about how consistent is the plan definition in our specification. So this is something. All that tools are really important for the engineers to make sure that. Or to make sure that the design is properly done and the routing the current routing can drive to can go to the production for the PCB. I'm sorry, I have to change. And finally, to perform the real measurement, we need, of course, instrument like a multimeter, scope. But in the case and in the context of signal integrity, we definitely need what we call a VNA, a vectorial network analyzer. This is a very important and mandatory instrument to measure the power of the high-speed signals going through the PCBs. It provides all what I showed before, and especially the S parameters. It will generate the real data of the circuits that will have to be compared to what we simulate earlier in the design. And then from this stage, if the simulation result and the real measurement are coherent and consistent, we can definitely go or have a green light to go for assembling and integrating the component on the board, and then provide the board to the hardware and software engineers to make the functional test. The conclusion of this presentation is that the latest requirement for powerful products, single board computer, Ethernet switches, FPGA board supporting rapid interface like 25 gig and 100 gig Ethernet is really ubiquitous. The new generation of system will really profit of all the benefits that are coming together with the new technology of components, materials, and of course tools, ecosystems. However, while the technical challenges are obvious, the time to market and the costing will have also to be mastered and considered. And for that reason, the system integration, the signal integrity simulation is really a good tools to go that way, because it will avoid to go in the wrong direction. At least it will give some good methodology to move forward and avoid material loss, new cycle of designs, and all what I try to describe all along this presentation. So, thank you. I hope that I have been clear enough. But so I leave the microphone to you,
Jamie.
Thank you so much, Mark, and thank you so much, Frank. A few of you have already submitted some questions, so we're going to jump right in there. But as a reminder, if you would like to submit a question, type your question into the question window on the side of the screen and hit the submit button. And our first question today is, will VITA 68.3 require vendors to measure the S parameters of the portions of channels that belong to their devices, whether these devices are plug-in cards or backplanes?
So,
Yep, I'll take this one. Yes, VITA 68.3 doesn't intend to require the vendors to measure the S parameters. You can do your homework and provide simulated S parameters. Of course, it's always a good idea to measure your boards as well and do a correlation analysis between your measured and simulated S parameters, and get out all the kinks from the results, so you're sure that what you measured is what you simulated.
Thank you. Will VITA 68.3 tell me how to design the breakout regions on my PCB in order to get 25G data rates?
I'll take this one.
Take this one again?
Yeah, the VITA 68.3 would not tell you how to design the breakout regions. That's a task for your signal integrity department. You have to go through extensive simulations to optimize the breakout regions. Again, you do your simulations, you do post-layout simulations. As Frank pointed out, those are the best because that's what you're going to get in the end. And again, after you've fabricated your product, it's a good idea to measure it to make sure that your results match your simulations and you're sure that your breakout regions are optimized.
Thank you. Are the reference models provided by VITA 68.3 available to anyone?
So I can take that one. When 68.3 is released publicly for trial use a little bit later this year, any VITA member is allowed to download and use both the standard document and the models that'll accompany the document. If you're not a VITA member, you're naturally free to purchase the standard and the models. They'll be packaged together, I'm sure, because that's how it was done with previous documents with multiple files like this. So yeah, when it's released for trial use, anybody can download it. Whether you're a member, you can download it for free, or it's available for purchase. Just contact VITA to work that out.
Fantastic. Thank you so much. That is going to conclude today's presentation. On behalf of Military and Aerospace Electronics, I would like to thank Elma Electronic for sponsoring today's webinar, and to our fantastic presenters, and of course, for all of you for joining. Have a great rest of your day.